Hello, my name is Dave Linder. I'm a software architect at MapleSoft. I'm here today to talk about numeric computations in Maple. Questions I often see by users involve how to make their floating point numeric computations perform faster in Maple. The answers often include references to special terms such as evalhf, the compiler, option hfloat. But a difficulty for the non-expert lies in knowing which of these techniques can be used and when. So let's try and clear up some of the mystery of the terms by discussing their functionality and how they compare. This document is aimed at the user with an intermediate level of Maple experience and knowledge. The special techniques used here can often improve performance dramatically, sometimes improving computation time by a factor of 20 or more. Let's review a few basic concepts. Maple is an interpretive language. The Maple kernel interprets and executes code. Normal, all floating point numbers are represented and stored by the kernel as software floats, which means that internally they're stored in memory in the same general structure used for symbolic objects. The acceleration techniques under discussion here all operate with some representation of hardware double precision floating point numbers. The key to the speed of these mechanisms is in the internal use of hardware floats rather than software floats. Software floats can have arbitrary precision, but hardware floats necessarily have double precision internal representation. A good place to start is by using procedures so that our computations can be computed easily for different input values. The examples below all use procedures, and some of the performance acceleration techniques under discussion require the use of procedures. The evalhf command provides an alternate interpreter in which all numeric quantities are stored as hardware double precision floating point numbers. Unassigned symbolic names cannot be handled directly in this special environment. In fact, under evalhf, there are a number of restrictions which allow much faster execution of code. Function calls and even basic arithmetic can be computed much faster because the restrictions entail that a great deal of Maple's internal machinery is not needed. There is a help page on the restrictions on procedures under evalhf, and another one documents which commands can be used directly from within a procedure running under evalhf. One reason that evalhf can compute so quickly is that it doesn't create temporary structures which have to be handled as collectible garbage by Maple's internal memory management system. Typically, the call to evalhf is wrapped either around an individual expression or around a function call. For example, evalhf of 7 plus 1/3 results in a hardware floating point result with approximately 15 decimal digits of accuracy. We can compute the result of a call to a procedure P by wrapping P of its argument with a call to evalhf. In this case, evalhf of P of 2.0 returns another hardware floating point result. Sometimes it's difficult to divide up a computation into the parts that can run under evalhf and the parts that can't. It may be that the most natural way to program a procedure entails some parts that do run under the restrictions of the evalhf environment and other parts which don't. In this case, there are other acceleration techniques which we can use. Option hfloat is a very general purpose acceleration technique. Option hfloat is an option that we put on a procedure, and when a procedure has that option, then all the floats used directly within that procedure are used as hardware floats. They're used as hardware floats of the form called an hfloat. An hfloat is a light wrapper around a hardware float. Such hfloats, temporarily created during the computation, are still collectible garbage, and they do entail memory management. But arithmetic can be done with them much faster, and many commands, such as trigonometric and elementary functions, can dispatch to fast methods much more quickly. An advantage of option hfloat is that it does not put the same kind of restrictions on a procedure that evalhf does. Amongst other things, this means that it allows a procedure to use global variables, lexical scoping, unassigned symbol names and operations, to make direct calls to non-evalhfable functions, to create matrices inside the procedure itself. Here's a second example, similar to the first, but now using option hfloat. The option is simply an option put inside the procedure definition. Now, when we call this procedure directly, we get a hardware floating point result back, the same as above, 15 decimal digits approximately of accuracy. Notice that both the results agree. In contrast, under Maple's normal interpreter, the float computations would be done with software floats. They would respect the digit setting of precision, and they would return results with 10 decimal digits by default. If we call the original function procedure p at the argument 2.0, we get back a result with 10 decimal digits of accuracy. The compiler provides another fast computational environment in Maple. The compiler command works by internally translating a numeric procedure into the C language, compiling it under the hood, and then linking to the resulting object. The compiler returns a new procedure which can be called just like the original, but which computes much faster. There is overhead in performing the compilation of a procedure initially, and in loading the compiler's runtime into memory the first time. But excluding such overhead, it's generally the fastest floating point computation environment within Maple. There are restrictions on its use, however. Its runtime provides fast internal versions of key commands which can be translated. The compiler help page details the restrictions on use. Several of the restrictions are similar to those of evalhf. For example, matrices must be passed in as arguments to the procedure. An important restriction on the compiler is that nested procedures cannot be compiled. Here's a simple procedure example from above, compiled. We take our procedure PR, we apply the compiler command to PR, which returns PC, which is a new procedure. PC can be applied directly to a float input and results in a hardware floating point result with approximately 15 decimal digits of accuracy. We can review a functionality table which allows us to compare the functionality restrictions on these three methods. The important restrictions that we can use to compare these are whether they can handle nested procedures, whether there's compiler overhead, whether variable typing is required on the procedure parameters, whether matrices and vectors can be created internal to the procedure, whether symbolic expressions such as unassigned names and lists can be used within the procedure, whether global variables could be used, whether the routine is parallelizable, whether there's collectible garbage generated during the function call to the procedure. As we can see from the table, option hfloat is the least restricted. Compiler is the most restricted, but the compiler is hands down the fastest speed performer of the bunch. The compiler does attain the best performance, which we'll demonstrate in an example. evalhf is second best in performance, but it's also the second least restricted. The overall pattern is a trade-off between flexibility and performance. We're going to use a Newton fractal as a case study for the relative performance of these methods. We're going to compare the evalhf method and the compiler method on the Newton fractal computation. And both of those computations are going to be computed in serial mode and in multi-threaded mode. In the multi-threaded mode, we will compute different parts of the resulting image concurrently, in parallel. The iterative process of the Newton fractal computation gives rise to an image representation. In Maple, a grayscale image can be stored directly in a matrix with hardware double precision float 8 data type. The computational procedures each work by populating this matrix with floating point values calculated by a looped iteration. A univariate polynomial uses the input. The computational procedures of this document work separately with the real and imaginary components. The real and imaginary components of a polynomial are now computed for illustration, and these formulae can be found within the computational procedures. First, we take a polynomial of degree 3, which we're going to interpret as being a polynomial in a complex variable z. We're going to compute the formula for the real and the imaginary parts of this polynomial. Then we'll take the derivative of this polynomial, and we'll take the real and the imaginary parts of the derivative. All of those formulas are used internal to the procedure. We won't go through the details of the procedure here because our central focus is on the relative performance of the methods. But it's a great example for these techniques. In particular, it's a great example for the parallelism techniques because the computation of each entry of the image, each pixel, is done separately from each other entry. So it's embarrassingly parallelizable. First, we're going to look at the results with no optimization technique at all. We're just going to make a straight call to our computational procedure, which is called here source Newton. The source for this routine and the source for all other routines used in this worksheet are stored in code-edit regions and can be viewed. We're going to compute the Newton fractal image at a size of 300. In order to focus on the computational time for doing the iterative method, we're going to create all the vectors and matrices in play, and we're going to pass them directly into the matrix so they can be acted on in place. This is also going to allow our procedure to be easily run under evalhf mode. So first we're going to run without any special optimization techniques. And when this version is executed serially, the timing report indicates that the real time of the computation is the same as the CPU time because there's a single computational thread. Nothing else is competing for wall clock time. Once we do the computation, we can use techniques in Maple commands to embed the image directly into our worksheet. We see here that the computation for the size 300 under no optimization takes approximately 10.5 seconds to compute. Now we'll look at evalhf optimization. We're going to take exactly the same procedure call and wrap it in a call to evalhf. We've taken special care to make sure that our procedure is evalhfable and that it satisfies the restrictions on evalhf mode. We get a computation time, a real wall clock time of around 1.5 seconds, which is a timing that's an improvement of the original by about a factor of 7. And a quick numeric test shows us that the two resulting images, the two resulting matrices, are almost identical. Next, we're going to create a version of the procedure which can be run in parallel. It's quite easily done after we notice that the entries of the image are each computed independently of each other. So we can divide up the computation by operating, for example, on only a subset of the rows of the matrix M. So first we're going to create a procedure. You can look at the source code in the worksheet. The new version of the code only operates on a sub-selection of the rows. In this case, we're going to operate on only the rows 20 to 95, which is 75 rows, 76 rows. In this case, the real time to compute the computation takes only 0.4 seconds, 393 milliseconds. That's pretty much as expected. Originally we had 300 rows of M to be computed. Now we're only computing 75 rows, so it makes sense that we're taking very close to 1/4 of the time that we originally had. And we can even view the partial results, just the strip of rows that we've computed. Using Maple's task parallel execution mechanism, we can run multiple instances of this new parallel procedure in parallel. So each of the calls to this procedure can compute over a different subset of the rows, thus building up the entire image. The method works by using a task, which examines the number of rows that are being requested, and if the requested number is greater than some key value, then it splits in half to make new tasks, each of which would go and compute 1/2 of the previous request. Eventually, of course, you have to stop and do the actual work. If the number of rows specified for any particular instance of a task is less than the magic cutoff value, then the procedure actually goes and does the computation and doesn't split again. The task mechanism allows the instances of the actual computation to be run in parallel, concurrently. So now, if we operate on the full matrix M and compute all the rows, all 300 rows, using this task model, we get a timing for the original computation with no optimization but parallelism of only 4.6 seconds. This was executed on a quad-core machine. We've got approximately 1/2 the time for the unaccelerated serial version. Next, we're going to run the multi-threaded task process in full to compute the entire image, but we're going to run it under evalhf. So now we compute the full range of rows, all 300 rows, using the task parallelism. We get a real wall clock time of only 4.45 seconds, 450 milliseconds. So this is around 1/3 of the time it took for the serial version to run under evalhf. The aggregate CPU time was around 1.6 seconds, but that's the sum of all the CPU times done by all the cores. We can even look at the resulting image and see that it's exactly the same as the previous image. Now we're going to turn our focus to the compiler. In order to use the compiler effectively, it's often necessary or prudent to place type information in the definition of the procedure, to put type information on the parameters in the function definition. So code edit region contains a new version of the procedure, the original procedure, where we've typed the parameters. We also give the new procedure a special option, threadsafe, which allows the compiler to return a compiled procedure which can be executed in parallel. The procedure is now compiled, and we get back a new procedure. We are now going to run the new procedure, but we're going to run it serially, and we're going to run it to compute all rows. It takes only 20 milliseconds to compute, which is a dramatic improvement over our previous results. We can even run the compiled version parallelized. As I said before, it's a new feature for Maple 18 that we can run compiled procedures, thread safe. We get a result, a timing result, which is again twice as fast as the compiled version running serially, approximately. Now we're only down to 10 milliseconds. So we went from 10.5 seconds down to 10 milliseconds. That is an improvement of around a factor of 1,000. The resulting image is exactly the same as the original. We can even look at a table which details all the timing results we have. What we see is that, yes, it's always a good idea, if you can, to use multi-threading. The performance factor of improvement for a quad-core machine can be somewhere between a factor of 2 to a factor of 4 if you're really lucky. But the really big difference comes in moving mode. The compiler is much faster than evalhf under optimal circumstances, and evalhf is much faster than the unaccelerated mode under best circumstances. So you can see by the factors of improvement that it's always in your best interest to switch from one optimization technique to the next best. And that's a bigger improvement than it is to go from being serial to being multi-threaded. So we can review our conclusions. The conclusions are that for intensive numerical computations, the efforts of adjusting your code to run in one of the accelerated floating computational environments is often very worthwhile. We can see here that the serial run of the compiled version is performing much better than the multi-threaded version under evalhf. Similarly, the serial run of evalhf runs much faster than the multi-threaded unaccelerated version. So for a particular application, it may be more beneficial to change the computational mode to the next best, if you can, than to compute in parallel, unless the number of multi-threaded cores that you have exceeds a number of 16 or whatever. There are several other more interesting aspects that can affect performance. For example, these computational procedures may perform better if the order of nesting of the double loop of the matrix entries is done in a different order. We can minimize cache misses that way. Or the task splitting could be done across rows versus columns. We could make the order of the nesting of the loops match the order of storage of the data. Is it C order or Fortran order? It's also possible that we would get different degrees of performance if we had worked with a complex value Z rather than separating the real and imaginary components out for each method. There's also the practical problem of how to get arbitrary formula into the looping body of the iterating procedure. These are great topics for further investigation. I hope you've enjoyed this talk, and I wish you happy computing.